This is an example problem of adding vectors graphically. The description that we have with the problem is a person is walking on a horizontal escalator, a moving sidewalk. If you've ever been in large airports like in Atlanta airport, they have moving sidewalks that help you go from one terminal to another terminal. The velocity of the escalator is 4.5 miles per hour, say east, and the person on the escalator can walk at a 3.50 mile per hour pace. So if we use our steps to add vectors graphically, we must first identify the vectors. In this case, I'm going to draw a diagram that helps us understand what is happening in this problem. We have an escalator, and the velocity of the escalator is going east, and it is 4.50 miles per hour. We have a person walking on the escalator. The person is also walking east in that direction, and the velocity of the person is given as 3.50 miles per hour. So those are our two vectors that we have. The next step, we must identify a scale. We want to make the scale as convenient as possible so that our vectors fit on the paper appropriately. In this case, I believe we can have a scale that's very easy to use. The scale is going to be 1.00 centimeters, which is the distance on the paper, is going to be equivalent to 1.00 miles per hour. Miles per hour is the velocity, but we're scaling it down because we draw arrows to represent a vector, and that arrow has a length. And so this 1 mile per hour is going to represent a length of a vector of 1.00 centimeters. So we've identified the scale. The next step, we use the scale conversions. Again, this is a simple process, but you should get in the habit of showing all these steps. So the velocity of the escalator converted to scale is going to be 4.50 miles per hour. And we want to convert that using our scale of 1 centimeter is 1 mile per hour. So the 1 mile, 1.00 miles per hour goes in the denominator. 1.00 centimeters goes in the numerator. Miles per hour cancel. We get the length of a vector that will be drawn to represent a 4.50 mile per hour velocity, and that's going to be 4.50 centimeters for that vector. We do the same thing for the person. The velocity of the person is 3.50 miles per hour. We convert that using our scale, and it's going to be 1.00 centimeters over 1.00 miles per hour. Miles per hour cancel. We should get 3.50 centimeters to represent the velocity of the person going east. Okay. So we use our scale conversions. The next step, we want to add the vectors tail to tip. And again, it does not matter the order in which you add the vectors, but I'm going to use, as long as you add them with the same magnitude and the correct direction that is given for their scales. So what we have here, we're going to take the velocity of the escalator. We're going to add it first. We have to have some starting point. I'm going to use this as my starting point right here. And so since our escalator vector is represented by 4.50 centimeters, which represents 4.50 miles per hour, we put our ruler up here, and we start the 0 right on our reference point, and 4.50 centimeters is going to be here. We draw that vector as accurately and precisely as we can, and all vectors are represented by an arrow. So this is the velocity of the escalator, which is 4.50 miles per hour. We then add the second vector that we have, which is the velocity of the person. We always add vectors tail to tip. I'm going to take the tail of this vector, 3.50 centimeters, and put it on the tip of the first vector that I drew. And it must be in this magnitude, and since it's also traveling east, it must be going in the east direction. Then we start at the tip of the first vector that we drew, put our 0 on it, and we'll make sure we draw the second vector going due east, and this is going to be 3.50 centimeters. I take my pen and draw exactly 3.50 centimeters, making sure we draw an arrow. So this vector, from this point to this point, is the velocity of the person, and that velocity is 3.50 miles per hour. The next step, We've added the vectors tail to tip. We now draw and measure the resultant vector. Remember, the resultant vector is drawn from the tail of the first vector towards the tip of the last vector added. So I'm going to put my ruler up here, start at 0, and I'm going to draw the resultant vector all the way from the tail of the first vector to the tip of the last vector added. I want to make sure I'm as precise and accurate as possible. Technically, I should draw this right on top of it, but I'm going to move this ruler just a little bit above it so you can actually see the vector that's drawn. It's going to be due east. I'm going to draw it from the 0 mark to this point. And we draw it as the resultant vector. This is the resultant velocity. And again, this resultant velocity should technically be drawn right on top of this vector. I just drew it above it so you can actually see the vector being drawn. I then measure that length of that vector. And if I get down close enough, you can see that a little better. And with this metric ruler, we can go 2 places past the decimal. If you notice, this tip is right at the 8 mark. Actually just a little bit in front of it, so I'm going to call that 7.98. So this vector, the resultant velocity vector, is 7.98 centimeters in length. I have to convert that. We drew that vector and measure the resultant. We use a scale conversion to scale back for actual velocity vector. I'm going to go 7.98 centimeters. I'm going to convert it. It's 1.00 miles per hour, or 7.98 centimeters. Centimeters cancel. And I end up getting I end up getting 7.98 miles per hour. So this is the magnitude of the resultant velocity. We're not done yet because we have to measure the angle, identify the direction. Well, the angle is easy. It's the direction that this arrow is pointing, and this arrow is pointing due east. So we have to say that this resultant velocity is also going due east. So both of these are part of our answer. 7.98 miles per hour and due east. Of course, we're off just a little bit on measuring due to error in measurement, but it should be real close to 8 miles per hour, but that's pretty good.